When I wrote this book, I wrote 13 chapters, ended up scrapping one after writing it. I decided to just focus on the universe is not expanding. I had a 13th chapter for, it's like an alternative cosmology, but it's a little too woo-woo. It's sort of religious. Like I talk about God and stuff. And I decided that was not a good place to enter it because, I mean, I've got some wacky views and I don't want that to influence this. The universe is not expanding. Like that was the topic of the book, so that's why I just named it that and tossed that chapter. I put all of my focus into the first 3, 4, 5 chapters, and everything else were things that I had to include. The last chapter I put a lot of focus in too. That's chapter 12, but chapter 11 is one of them chapters. It's like the BAO and observational evidence and predictions. Like these chapters were like, it's things you have to include. And when I wrote through, like basically all of the notes that I wrote were arguments against this. Like, I don't want to talk about stability of the universe. I don't want to talk about baryonic acoustic oscillations. I don't want to talk about predictions, and I don't want to talk about observational data. The only thing that I really want to focus on is the ontological existence of space-time and this idea that mass density has scale dependence, and so you can't use homogeneity. I will personally never be able to understand perturbing a cosmological model because it's not a rational practice, okay? When you set up a cosmological model like Einstein did his initial model. Now, we got to give Einstein credit. Like, he did amazing work. I'm not mocking Einstein here. That would be silly. Everything he did was absolutely amazing. This is like the one area he just didn't know what to do. It was because this is new. It's a new thing. It's weird. There was a lot of weird ideas. Like I said, Einstein didn't even know there was galaxies then. And so what he did, he just assigned a homogeneous mass density to his model so he could do the equations. And then he set up he balanced the Einstein field equations using his homogeneous model, and that's fine. He's done. But like, you want to do something. You want to see what it does. But if it just stays homogeneous, then it does nothing. It just does nothing. And so he set up you perturb it, what's called introducing perturbations. And these are like small segments. So, you can pick whatever parameters you want to do this, but usually you want to do something realistic. So the pressure, you just see what happens when you add a little bit of pressure to it and change the density somewhere. And when you do this, the universe collapses. It doesn't really collapse, though. This is nonsense. Introducing this perturbation is actually a violation of the Copernican principle. It doesn't matter where you do it. If you perturb the universe here, it collapses everywhere. And so it's a mathematical gimmick. Like, this is not how the universe introduces perturbations. The universe is just already existing. It already exists, and whatever mass density you want to assign to it, that's not correct. Because as soon as you assign a mass density to the universe, you're choosing a preferred scale. You're just saying this scale is this dense. Okay, that's fine. But there's, whole infinite universe. If you perturb the universe here, and I perturb the universe in 1 trillion to the trillionth billion light years away, like, just pick the most absurd distance a Google amount of light years away, like whatever the most absurd number is. Googleplex, is that it? I don't know what mathematicians just make whatever things up that they want. I'm going to create, my new number is defined as whatever the largest number is plus 1. And we'll call that Brown's number, okay? So whatever the largest number is plus 1, that's Brown's number. Anyways, and we do Brown's number to the power of Brown's number. And so you perturb your universe at that distance away from my universe. I mean, it's the same universe. It's different locations. You're located over there and I'm over here. And we both end up with a large star that quickly grows into a black hole and it exponentially grows until it runs out of mass. And then they start going towards each other. But it's going to take a long time for them to get to each other because we probably our black holes may be 1/2 of a Brown's number in mass at that point. Anyway, and so it collapses into a single point. But this is not cosmology. You're doing general relativity, but you're not doing cosmology because you're just assuming a homogeneous mass density, which is not real. In this situation, you can do that if you want, and I guess it would be a cosmological model. It just doesn't do anything because you're not going to introduce perturbations because the perturbations take away from the homogeneity. So your universe is no longer homogeneous. And so really you could have just started there. You didn't have to introduce perturbations. You could have just started with the universe slightly perturbed. And it doesn't work. It doesn't work. It works as in this is what objects do. If you just look around a star, this is what's happening. It looks like the star is collapsing. It's not really because there's a whole nother universe. And this universe is scale dependent. This is what Einstein was missing, is the scale dependence of mass density. Because if you want to assign a special mass density, then you're violating the Copernican principle. And so you're definitely going to have collapse. The Copernican principle, if you're unaware, I don't know if I've explained it yet or not. It's basically, it's evolved through the years. It used to be that, there's no, that the Earth is not the center of the universe. And it evolved into modern cosmology as basically saying that you're choosing a preferred frame of reference. And by doing this, you're violating isotropy. The idea that you're not really violating isotropy, but you kind of are, because it's essentially the same as ignoring the rest of the universe. Or it's like we have this idea that the universe is about the same everywhere. That this is the idea. Like about the same is the best way to explain it. In other words, if I go to one Brown's number light years apart from us and look, I'm still going to see stars and galaxies and planets and comets. And there's going to be an observable limit. That's the idea. And so when Einstein assigns homogeneity, he's violating that there. But he's also, and like cosmologists always claim the universe is homogeneous. They just make this assertion and it's obviously not true. It's obviously not true. And so it's easy when an expert says this and then you say, oh, that's not true. They'll just respond with like, well, it's statistically true. We're searching for words. The word they're searching for is that mass density is scale dependent. And that there's gravity also. So mass also has gravity. And so there's this pull from all points. I don't know how else to say it. Like it's not it's a complicated thing. Like it really is hard to think about and to visualize. And my argument is that once you accept that the universe is not homogeneous, once we just throw that definition away, now you must, absolutely, there's no other way about it, define R from 0 to infinity. Or at least an observable limit, because there is a Schwarzschild radius, a horizon. There's going to be a Schwarzschild horizon, no matter what. Anyways, and once you define R, like there's basically only one solution for isotropy. Once you define it this way, I've got a new visual that I'm adding to the website. If you want to go there and check that out, I'm going to actually pull it up during this video and click around and show you how it works. But you can click the link in the description, and I used Claude to make this, and it was really, I really like the way it turned out. It's a helpful way of visualizing the what I call the sphere of influence. This is the amount of mass that impacts the geodesics of the light wave. Now, this profile is stable. This is a stable model, but that's not really the argument I want to make. I don't think stability is, for one, lambda CDM is not stable. So why does every other universe have to be stable? Like, what is this? Like, anyways, I think that's enough. I think I got my point across. Let's go on to the next chapter. It's my favorite.